Hello and welcome to the first lecture video for Chapter 4. All right, so in Chapter 4 we're going to talk all about motion in two dimensions. So the big picture, right, is we introduced motion 2 chapters ago, defined velocity and acceleration, talked about 1D cases. Then we had a whole chapter where we introduced vectors, vector addition, components of vectors, as well as additional material of vector multiplication and in both the scalar product and the cross product. But now we're going to circle back around to position, velocity, and acceleration, but using our new tool set of vectors. All right, so let's get started with that, talking about the introductory sections of 4.1 and 4.2. In these introductory sections, they're introductory in the sense that they're not any of the special important cases, namely projectile motion, circular motion, or relative motion, which are going to be kind of the three big topics of this chapter. But they're not introductory in the sense that they're particularly easy problems. They're just general vector problems that involve I hat, j hat, k hat notation, often 3 dimensions. So they can have a lot of complexity to them, despite being kind of the basic knowledge level of physics, right? So mathematically they may be complex, but physically they're simple, okay? So there's really no new key terms, and even the key formulas are something we've sort of seen before, but we haven't seen in the vector sense. So first of all, we just have displacement, all right? This is just some change in x and y. So r represents, just basically a resultant or a hypotenuse length, all right? Of course, it's a vector, and it's composed of I hat, j hat, and k hat components, which is the change in x and the change in y and the change in z attached to each of those components respectively. Okay, so now we're going to take r, at least the instantaneous value of r, and take its derivative with respect to time to get velocity. What that would look like would be dx over dt times I hat, dy over dt times j hat, and dz over dt times k hat, okay, or in the k hat direction. And what this is the velocity vector. All it is just velocity, so speed and direction in 3 dimensions, okay? And just each one being the first time derivative of the displacement in that direction. So it's the instantaneous change in x in the I hat direction, the instantaneous y in the j hat direction, and so on. Okay, and remember that I hat, j hat, and k hat are unit vectors. Review the last chapter if you're confused about that. All right, here we have the velocity vector, just expressed in terms of its components, right, instead of in terms of derivatives with respect to x. Okay? All right, then of course we could take the derivative of velocity to get acceleration. So this is the acceleration vector in 3 dimensions. Same idea as we did to go from position to velocity. We're going from velocity to acceleration. You take the first time derivative of the x component of velocity with respect to time, the first time derivative of the y component of velocity, and the derivative of the z component of velocity with respect to time. Okay? And of course, each one is attached to its respective direction. And we can also just write it as a sub x times I hat, a sub y times j hat, and a sub z times k hat. Right? So that's it, kind of what you would expect for taking position, velocity, and acceleration and considering them in vector form. Okay? So we have 2 types of problems. We can really kind of maybe simplify them to one type, but I did realize that we have types of problems that involve constant acceleration, and those are ones where we can use the kinematic equations like we saw 2 chapters ago for free fall, for example. These are kind of pre-made equations, don't require any calculus. They can be derived of calculus, but since constant acceleration is so common, they're often useful equations to remember and use. And then we have more complex problems where the acceleration is non-constant, thus we cannot use the kinematic equations and we always have to integrate. The first example is the type 1, so it's one where you could use the kinematic equations. I went ahead and actually just used integral calculus, but it was a bit of a kind of an overkill approach to solving the problem. An object moving through space has an initial velocity of v naught in the I hat direction, okay? So the initial velocity is entirely in the x direction. All right, it experiences a constant acceleration of 2.54 meters per second squared, but where does that acceleration point? It's not just enough to say there's a constant acceleration because this is a 3D problem, not a 1D problem. Well, that acceleration is pointed directly halfway between the positive z-axis and the positive y-axis. Okay, so we got an x-axis velocity. We've got a z-y plane acceleration. What does that look like? Let's draw a picture. Okay? So here's a picture of x, y, and z. Okay? You can clearly see the initial velocity pointing entirely along the x-axis. Okay? And here we have acceleration, which is in the yz plane at that 45-degree angle between the two. Okay? So that's telling us that velocity is not in that plane at all, right? The initial velocity. But of course, what's going to happen is that initial velocity is going to that constant acceleration is going to cause the velocity to turn. Because over time, the velocity will become closer and closer to parallel to the acceleration. Okay, given enough time. Okay, does that kind of make sense? But let's see. Let's just run through the numbers. So we go ahead and write the acceleration vector in terms of I hat, j hat, k hat notation. There is no I hat because the x component of acceleration is 0. So there's only a j hat, k hat component. And all we have to remember is that we can split take the information we're given about the hypotenuse or the magnitude and the angle relative to a particular axis and just then turn those into components. So in other words, it's just the y component and the z component of acceleration. Okay? And cosine and 45 and sine 45 respectively. Not that it matters for 45, right? Because of the symmetry, they're swappable. Okay? All right, and then we're going to say, okay, well, to get the velocity, if I know acceleration, I could integrate each term to get velocity. Okay? Now I could have also used the kinematic equations because since the acceleration is constant, I know that the velocity must be linear. But indeed, the integral, of course, gives me that same result. As we think about it, if I plug in a constant, because a sub y is, after all, just a number, and then I integrate it, I just end up with t. It's a definite integral. I'm integrating from 0 to t, okay? Because I know that the initial velocity in the y and z directions are 0, so I don't have to worry about a constant of integration or anything, okay? And so then I simply have that expression there, all right? And over here, I also integrate from 0 to t, but here the acceleration in the acceleration in the x direction is 0, but here the initial velocity is 12.5, right? There's a non-zero initial velocity. So essentially you can think of each of these as we integrate, picking up because by definition, all of these are going to be v minus v naught, okay? But as a vector, okay? And so really I could have, on the left-hand side, wrote v vector minus v naught vector. And that would have kind of clearly shown why we have a 12.5 on the I hat, but not on the j hat and the k hat. So I hope that's not confusing. And again, we've seen that notation before in a single direction or dimension. It just looked like this. Okay? And all we've done is just change that to a vector. Okay? All right? But again, it's totally in agreement with the kinematic equations, linear velocity, and then constant velocity where the acceleration is 0. Okay? I could also have gone over to position. If I'd gone over to position, I would just get more things that look like the kinematic equations, right? V naught x times t. I would get a 1/2 t squared and a 1/2 t squared, and then ax, ay, az. Okay? So absolutely consistent with the kinematic equations, especially because v naught y is equal to 0 and v naught z are equal to 0. Okay? All right. And then, of course, ax is equal to 0. All right? But then we can just clean this up, right, by calculating cosine 45 and sine 45, multiplying it by the magnitudes of acceleration. And here's our final velocity. All right? Oh, and specifically at 4.62 seconds, because that's where we're asked. Right? So then we find what has happened, right? Let's think about the picture here. Well, the x component of velocity hasn't changed. The y and z components have grown, both in the positive direction, because the acceleration points in the positive direction of those two axes. And that means what's happened is it's curved in that plane, right? It's curved into a plane that's sort of parallel, or something like this, right? It's curved up and it's starting to become, the velocity that is, and starting to become more parallel to this line. Okay? All right, let's do something similar. All right, this one will definitely just be using integrals because we have position functions that are polynomials to the third power. that tells us right away, if we take two derivatives, that our acceleration is going to be linear. A linear acceleration is not a constant acceleration, so you can't use the kinematic equations. All right, this is a 2D problem. A wheeled robot is programmed to follow the following two-dimensional position functions while navigating a smooth flat surface. Okay, and note that x and y are measured in centimeters. At t equals 3 seconds, what is the robot's position vector r? What is the angle this vector makes with the negative y-axis? So that would be this direction. Okay, so let's do it. Now, right here, I've just used a graphing program to graph the position of the robot in x and y over time. So you can think of this as like a parabolic expression here, all right? And this is for t from 0 to 5. Notice the axes aren't scaled the same. The y-axis is scaled much larger than the x-axis. All right, these are all the vectors we're going to concern ourselves with. The first one we're looking at is just going to be r. So you can, for now, ignore v and a. We just care about r. All right, but let's find r. Okay, and we specifically want to find r after 3 seconds. That should be easy, right? I should just be able to plug in 3 into my expression. Okay, so I simply plug in 3 seconds for x, for the position function in x, and I get 29.5 meters. Okay, so that's where the green dot is right there. That's about, looks consistent with the picture. All right, and then I do the same thing for the position function y, and I get negative 132. All right, looks good. All right, so that's my location at t equals 3 seconds. All right, now what if I want to, and that, by the way, that's going to be r. I'll show you in just a second. What if I wanted to find theta? And I know I want to find theta because that would be the angle with respect to the negative y-axis. In that case, it's opposite over adjacent, which would be r sub x over r sub y. All right, so that's going to be, and then if I want to isolate theta, I take tangent inverse of that ratio of components of r, and I get 12.5 degrees. Okay, they might be like, that doesn't look like 12.5, but again, remember that the vertical axis is scaled much differently than the horizontal. All right, and then finally, just taking the information about r and writing an I hat, j hat notation, and remembering to then identify the units as centimeters, we find that r, this vector that has this length and direction, is 29.5 I hat minus 132 j hat. And it doesn't matter where we put r, we can have it start at the origin like this, but of course vectors are the same no matter where you put them. We could have the vector over here and it would still be r. All right? Good reminder about vectors. Well, what are we asking for in part B? So part B, same thing after 3 seconds, so we're going to be concerned ourselves with that green dot again. What is the robot's velocity vector v, and what angle does this velocity vector make with r? All right, cool, we can do that, right? So one thing is we know that, since we kind of drew it to scale here, that this dot is the point at t equals 3 seconds, right? Give or take. And then that means that the velocity, since velocity by definition is tangent to trajectory, it's tangent to where you're going, that is the definition of velocity. Just think about the fact that it's composed of tangent lines. So if it's composed of tangent lines of a function that is moving in multiple dimensions, it still is the tangent vector, okay? As opposed to the slope, when it was just 2 dimensions. All right? And so this, we know that the velocity must point tangent to the curve at that point. So that gives us an anticipation, a expectation that v should probably have almost no x component and a large y component, or at least a substantial y component. All right, so let's just go through the process. So we're just going to take our two functions, our x and y functions, and just take the derivative of each with respect to time. So you can see I'm just going to do vx and vy. All right. All I've done here is just take derivatives, right, following the derivative rules of polynomials. Okay, and then clean them up a little bit. All right, at least clean up the second one because I had negative 3 times 0.67. I want to clearly show that that is negative 2.01. All right, there isn't really much work required for the first one, at least not a second step, right? There we go. I guess it probably actually was the same number of steps, just shorter. All right, and then I'm just going to plug in 3 seconds. So all I'm going to do is take these two time-dependent expressions of velocity, it's two components, and just plug in 3 seconds for each. And that's all I'm showing here. V sub x at t equals 3 and v sub y at t equals 3. And I'm going to go ahead and do that all in one step, expressing it as a vector, because I'm putting those functions attached to their respective I hat and j hat components. So that's the thing, right? The coefficients that we multiply by the unit vector can be themselves functions. No problem, right? Absolutely they can be. All right, so I'm just plugging 3 seconds into each of them. All right, do the calculation, and I get 1.93 I hat, so a very small x component, and negative 62.7 j hat. Indeed, a substantial negative y hat component. Pretty consistent with this vector sketch that shows it pointing more or less straight down, right? And the units there would be centimeters per second. All right, and then I just want to find the angle of that vector with respect to r, I believe. Yep. All right, so with that, we'd use the dot product for. So good reminder about finding angles with the the scalar multiplication of vectors, otherwise known as the dot product. I mean, are there other ways we could think about it? I mean, yeah, we could think about the components and kind of draw other triangles. So we could go through and systematically draw triangles and think, and instead of doing it with the dot product, both approaches are fine. But we'll use the dot product here. So by definition, v dot r is vr times cosine theta. V and r are the magnitudes of the velocity and displacement vectors. All right, and then I'm just going to isolate theta by taking cosine inverse and divide both sides by the magnitudes. Notice here that I'm dividing by the magnitudes. Up here, this is actually still the dot product. I should have put the notation there. All right, so these are the magnitudes, and this is the dot product. Okay, and so this is what it's going to look like. Remember, when you take the dot product, you just group together the components, and the result is a scalar. So it's vx plus vy and then in the denominator, it's just going to be the Pythagorean theorem, in other words, the length of v and the length of r. All right? We plug in all our numbers. All right, these are all the numbers that we've calculated in previous parts of the problem, and we finally end up with 8,000 over 8.4 and an angle of 10.9 degrees. Okay, so what does that angle represent? Okay, it represents this angle right here. Right, that's the angle that we found, and that's why I went ahead and moved v over to here so we can clearly see the angle that we're measuring. All right, it's not an angle measured in sort of the counterclockwise direction like typical of the unit circle. It's just going to be the angle between the two vectors when their two tails touch, and that would be this angle. Right, and you can see that angle is 10.9, which indeed is a little bit less than 12.5. Neither of which look quite to scale due to the asymmetric scaled axes, but definitely the fact that it's slightly less than 12.5 makes a lot of sense. Okay, so good reality check on does that answer make sense. Finally, in part C, I ask at t equals 3 seconds, what is the robot's acceleration vector A? All right, so now we're going to find this acceleration vector. Now, one thing about acceleration vectors is that by definition, because they represent the instantaneous change of velocity, and because the velocity vector is always tangent to the path, acceleration vectors always point inwards on the curvature. Okay? Now, if the velocity is growing a lot at that particular moment in time, then the acceleration will still point inwards, but it might point mostly parallel to velocity. On the other hand, if velocity is shrinking dramatically in magnitude at the moment that it's turning, then the acceleration might point mostly backwards, but still technically inward on the curvature. If the velocity is more or less constant in magnitude and just changing direction at that particular moment in time, then the acceleration basically points straight in on the curvature. And we'll see in another section of this chapter, of chapter 4, that idea, those components of acceleration, specifically when the curve is circular, which of course this curve isn't, those components are called the tangential and radial components. But the idea applies to any curve. It's just more elegant and specific for circular curves. And maybe simpler to calculate, maybe not, because we can always calculate it for any curve just using the integral definitions. Okay, so not to get kind of lost in the details, the key idea is acceleration always points inwards on the curvature of the path of the object or particle. Okay, but we can just solve it. We're just going to find our acceleration function and our acceleration function x and our acceleration function y, and we're going to evaluate them at 3 seconds each. Okay, so all we do is just take the derivative. All right, so here I'm really setting up to do it, all in one step. Clearly writing it in this function notation on each step, even the integral itself. Right. So now the derivative. Excuse me. I'm taking the derivative with respect to time of the function vx evaluated at 3 seconds. I'm taking the derivative with respect to time of the vertical function of velocity evaluated at 3 seconds, all right? And I'm acknowledging that both of them are vectors, right? So a lot kind of expressed there all in one. All right, when I do this, I'm then going to show one extra step. I'm going to show that the x component of acceleration, which is just taking this original function and taking its derivative with respect to t, time, twice, I just get negative 2 times 1.23 times t, which is just negative 2.46t. And then I do the same thing for y, and I'm going to get the negative 4.02 t minus 4.2. So this one ends up with another expression. This one is just a line without even an intercept. All right. This one essentially tells us that at t equals 0, there is a y component of acceleration, but at t equals 0, there is not an x component of acceleration. All right. But again, we can see that by just looking at our polynomial expressions of position and taking the derivatives twice. Okay. So then finally, I'm just going to take those two functions, evaluate them at 3 seconds. All right. And that finally gives me my acceleration vector. It's got a negative I hat component of length 7.38 and a negative j hat component of length negative 16.3 units centimeters per second squared. All right, does the fact that it points in the negative I and negative j directions make sense? Yes, it does, right? Because we expect it to point inward on the curvature. We expect it to point in the negative y direction because the velocity at this moment in time is growing in length as well as turning. And there we have it. All right. So, I say a lot of stuff about my expectations and how this all makes sense, but that of course comes with practice. But ultimately you can always fall back to the fact this is very procedural and you can just follow the rules of derivatives, in this case, since we started with position, and just go through, make sure you acknowledge the vectors, and make sure you draw pictures, because that's a good way to check your work and check that it makes sense. Okay, one final example. A particle's acceleration vector is given by a equals 13.2t minus or plus 9.81. Okay, all right, meters per second squared. If the initial velocity of the particle is negative 125 in the j hat direction, meters per second, and the initial position of the particle is 555 minus 1440, then how much time does it take the particle to reach a vertical position of y equals 0? Okay, just think about it, right? So we start with some horizontal initial position. We start with a negative vertical position, all right? So our initial position in the y direction is negative. That means we're going to be moving upwards because we're going to have to go back up to y equals 0. However, our initial velocity is moving us downwards. So how are we going to get back up to y equals 0 starting down below y equals 0 if our initial velocity is down? All thanks to acceleration. Because if you look at the component of acceleration in the j hat direction, you see that it is indeed positive. All right, so that's going to eventually bring us back up and then bring us back up to y equals 0. Also note that this is a 2D problem, all right? And this is a non-constant acceleration problem because we can see that in the I hat direction, in the x direction, acceleration is linear. It's continuing to grow, not remain constant, all right? And this one looks a lot like gravity in j hat, but this must be a coordinate system where positive y is measured up because, well, gravity is positive, all right? Or maybe it's just not gravity and happens to be 9.81. Okay, so here we're just going to acknowledge basically the definition of velocity. All right, that v minus v naught is this equal to the integral, the definite integral evaluated from 0 to t of the acceleration function integrated over time. All right, and then we're just going to use that to find our velocity function. All right, now notice, unlike the previous problem where we started with position and we're able to find velocity functions and specifically velocity function vectors by taking derivatives, here we started with acceleration and we have to then use integrals to get our functions. In this case, our unknown functions are velocity and position instead of velocity and acceleration. And since we're taking integrals, that's why I had to be careful to make sure to give you all the initial information that allow you to actually solve those integrals without unknown constants of integration. All right, so we got v minus 125 in the j hat direction. All right, notice v here. V is really a vector, by the way. Okay, excuse some of my slip-ups in notation here. It really should be like this. Okay, and then we have 1.35 over t times t squared. All right, and let's see. Oh, that's a dumb mistake. That should be a 2, not a t. Okay, that is not supposed to be a t. That is a 2, and I fix it on the next line. All right, so let's go ahead and do that. So you'll 2 lines down. We're going to do the same thing for position. All right, And what I'm doing here is I'm going to then sort of set this up the same. So my first step here is I'm just acknowledging that r minus r naught is, again, r vector, and then r naught is 555 I hat, and then negative 1440 j hat, okay? And then that's going to be equal to 6.75. And where's the 6.75 coming from? Well, it's the 13.5 divided by 2. Because again, that should have been a 2, not a t. Okay? And all right, and then same thing here. At this point, I've moved my 125 over to the j hat because it's on the j hat, just like the 9.81t. Okay, so here's our full function that we're going to integrate. Okay, I haven't moved over the constants yet, but I will. All right, so then we finally do that, and right, that's going to allow us to solve for, because it's actually in the first one, how much time. Okay, so in this first problem here, I'll take is we look at our two components. They're both functions of time. Right, so this is our position as a function of time in the x direction, and our position as a function of time in the y direction. Right, in the x direction, the function is a third order polynomial, and because the acceleration was linear, and it's a second order polynomial in the j direction because the acceleration was constant. So this one technically we could have used the kinematic equation for. All right, and the one I care about initially is in fact the y one, the one where the acceleration was constant. So all I have to do is just set just this function that's attached to the j hat unit vector equal to 0 and solve for t. All right, so that's all I'm going to do here. And when I solve for t, I get 34.1 seconds. So that's telling me that this particular particle will take 34.1 seconds to get to a location of y equals 0, starting with an initial location of negative 1440 and the other initial conditions of negative velocity and non-constant acceleration. Okay? All right. So then what is the horizontal position of the particle when this occurs? So all I'm going to do now is feed forward the information that I solved from part A, the fact that I found that it takes 34.1 seconds, feed that into part B to find out how long or how far it's gone after 34.1 seconds in the x direction, right? In the I hat direction. Okay, so then I'm just going to look at the x component of my position function vector. All right, and so I get my 6.75 divided by 3. I haven't calculated that yet. I'm just leaving it 6.75 divided by 3. And of course, the 3 just comes from the rules of antiderivatives for polynomials. Plug in my time of 34.1 and my 555. All right, and there we go. So, all right, it will have gone 8.98 times 10 to the 4 meters by the time it returns, or not returns, but by the time it gets to a vertical location of y equals 0, right? So in other words, that means that it's gone a lot further in x than y, because in the y direction it's only gone 1,440 meters, but meanwhile in that same amount of time, it's gone 89,800 meters in the x direction. And we can actually even write that in kilometers as 89.8 kilometers, okay? All right, so let's finally look at part C. What is a particle's velocity and angle above the horizontal when this occurs? All right, so now we're going to use the velocity function, which before was just an intermediate step to go from acceleration to position, because initially we only really cared about this position function here. But now we're going to take a look back and actually use our velocity function. Okay, but again, remembering this is a 2, not a t. Okay, and I've cleaned it up a little bit. I've rewrote it as 6.75. All right, I'm going to plug in that particular time of 34.1, because that is the time when the particle gets to a vertical location or position of y equals 0. All right, so, and it says here, like when this occurs, well, this occurs is getting to y equals 0. All right, and so we'll just then find the values. So now I just have in meters per second the x component of velocity, and in meters per second the y component of velocity. Okay, so then it's just a matter of finding the angle, and we want the angle above the horizontal. So then in terms of tangent being opposite over adjacent, opposite should be y, adjacent should be x. All right, so first of all, we're going to find the magnitude. So it says what is the particle's velocity and angle. So when asked for, I could have said what is the particle's magnitude of velocity and angle. So because that's with the way it's asked, velocity and angle, that makes me think magnitude and angle. All right. So the magnitude is 7,850, And that is again because the j hat component is so much smaller than the I hat component that these are almost the same, right? So in other words, the velocity is almost entirely in the x direction, which shouldn't be a surprise because it sure went a lot further in x than y, which means it's moving a lot faster in the x direction than the y direction. And then let's go ahead and actually find that angle. So opposite over adjacent, tangent inverse. And, right, oh, it's going to be a really small angle. And indeed it is. It's only 1.53 degrees. Just again, a testament that by the time our particle is at y equals 0, it is almost moving entirely horizontally. All right? And that's really, you can kind of guess that just based on the fact that acceleration is linear in the x direction and constant in j. And that means that this one is just going to continue to grow, the acceleration in the x direction, whereas the acceleration in the y direction is fixed and will eventually get washed out by the continued growth of the acceleration in x. Okay? So, right, definitely another example of kind of what we're talking about when we work with functions here. And hopefully all of these examples together have just given you a good idea about using vector notation and considering position, velocity, and acceleration as vectors. Again, in the rest of this chapter, we're going to look at specific cases that apply to maybe more real-life situations that are less abstract. Okay? All right, well, thank you so much for watching this video, and stay tuned for more throughout the week.